Good evening, everyone. My name is Luke Forman from Curtin University. I'm also a vacation student with Rio Tinto Iron Ore, and tonight I have the privilege of sharing special protection schemes for power systems. Just a quick overview of my presentation. I'll begin by identifying the need for special protection schemes, followed by some important definitions. I'll then give an example of an SPS in use in the Taiwan power system, followed by my own SPS, which was developed for my final year project, as well as the works I have planned for the future. So we all know that electrical faults do occur, and when they occur on power systems, such as distribution networks, they can result in severe damages, not only in terms of damage to generators or bus bars, but also in terms of lost production, for example in mining companies with their downtime. These costs can run into millions of dollars, and thus there is a strong need for reliable but good protection schemes. There is a need for reliable algorithms which can monitor key system parameters and mitigate the negative of faults. And thus the solutions proposed in this presentation fall into the category of special protection schemes. This is the Rio Tinto distribution network in WA. We have 14 different mine sites throughout the Pilbara. Here at Parabadoo and Urulimai Power Station, those are the two main sources of generation. And late in 2011, there was a single-phase ground fault between Brockman and Millstream. And usually this isn't a big deal. The conventional protection schemes, the distance relays, differential relays, can take care of the fault. But one of the reverse distance relays malfunctioned. And as such, there was a great outage in the Pilbara, and it even affected places such as Tom Price, even though it should have just been localised. This is data obtained from Network Manager, which was obtained in real time. It shows the frequency against time during the event of the fault. Here's the steady state condition. It's about 50 Hz, which is what it should be. But in the event of the fault, the frequency drops to about 49.5 Hz. So clearly, this is an abnormal system condition, and this information can be used in the development of a better protection scheme. So again, the SPS, or any special protection scheme, is designed to detect abnormal system conditions, and thereafter implement pre-planned remedial actions in order to increase the stability of the power system. These remedial actions can take many forms, for example, generator tripping, or load shedding, or some other system separation. This schematic is a general representation of a distribution network. The circles are generators, the vertical lines are bus bars, and the other lines are distribution lines. This rectangle here, the control centre, is the guts of the SPS. We can see that the data from each of the generators and bus bars is being sent to this control centre, and thereafter the reliability algorithms determine the remedial action. The system can be simplified into a two-system network, where we've got the non-critical machines on the left-hand side and the critical machines on the right-hand side. This model can be further simplified into the one machine infinite bus system, where we have the infinite bus here, which represents the external network, and this machine representing the critical machines. In order to ascertain system stability, the equal area criterion analysis was performed, and basically, if the area on the right-hand side exceeds the area on the left-hand side, then the system becomes unstable. Now onto my final year project. The key stakeholders for this project were Curtin University with the academic interests, Rio Tinto with the commercial interests, and the German company Dix Island, who developed the Power Factory software used in the project. The requirements for my algorithm were for it to be fast, reliable, and capable of monitoring a wide range of system parameters, including voltage, electrical frequency, and power angle. The specifications for my project depended upon the algorithm produced, but the most important one is the mitigation time. It has to be somewhere between 5 cycles and 10 cycles, which corresponds to 100 milliseconds and 200 milliseconds on a 50 Hz system. For my project, I investigated 3 separate problems and developed 3 separate algorithms. The first problem considers two faults on the distribution lines in separate locations. The second algorithm considered a three-phase fault on a generator, and the third was the unexpected loss of a distribution transformer. For the sake of my project, I had to make several assumptions. The first was the most severe fault type being a three-phase line-to-ground fault. The reactance to resistance ratio was assumed to be 10:1, which is consistent with most distribution lines. The AVR files, or the automatic voltage regulator files, and governor files were assumed to be developed correctly, and perfect communications was assumed amongst the SPS elements. In order to test the algorithms, I had to come up with some sort of test bench, and the test bench chosen for this project was the Warden-Hale 6-bus model. The Warden-Hale 6-bus model has 2 generators, 6 bus bars, and 3 loads, and was therefore sufficient for this project. Arbitrarily, I chose 2 of the loads to be critical. That's the load at bus 3 and bus 5, and the load at bus 6 was nominated to be non-critical. In order to verify the stability of the network, I had to execute a load flow. It's evident from this graph that bus 1 and bus 2 are the generation bus bars, whilst 3, 5 and 6 are the loads, and bus 4 is a transfer bus. This schematic illustrates the algorithm I developed for the first problem. Basically, I've got 2 distribution lines being at fault, one here between bus 1 and bus 4, and another fault between bus 1 and bus 6. If the SPS is not in use, the system is able to restore to the steady state condition. As we can see, bus 2 supplies a significant amount of power, so even if we were to lose generator 1, it is still able to satisfy 70%. However, if the SPS is in operation, by controlled load shedding and the utilisation of capacitor banks, we are able to satisfy 98% of the critical load. That's shown in this table here. Without the SPS in operation, only 7%, but with the SPS, at least 98%. In the development of the second algorithm, it was necessary to use transient analysis in order to work out the maximum power angle, and it was found that after 137 milliseconds, the angle was 82 degrees, but after 139 milliseconds, the power angle was 102 degrees. So the maximum power angle was found to be, maximum volt duration was 137 milliseconds. In the future, I plan on developing more sophisticated algorithms on larger networks, such as the IEEE 14 bus, and after that, exporting these algorithms onto the Rio Tinto distribution network. Thank you for listening. Yes?
How close would the special protection system be to the actual faults? I imagine that this sort of control signal has to travel to somewhere to perform the correct action, and then with such small periods of time, I'm wondering if the speed of light becomes too slow.
Yeah, speed is a major concern with SPS. Unlike conventional protection schemes or normal controls, it won't go through the Rio Tinto Operation Centre. It will be placed locally on the power system, and as such, when you're monitoring the bus bars or the loads or even the generators, we can access those values in real time. For conventional protection, usually we're good if it's in 100 milliseconds. So if the fault is, say, somewhere between 100 and 140, the SPS should be able to do its job. Yes?
How difficult or easy is to implement this in a real system? You're saying my algorithms will be implemented in Rio Tinto. What is implied in that? What do you need to do to implement your algorithms in Rio Tinto's network?
In order to verify the merits of the algorithms, you have to have much more realistic values obtained. What I'm doing here on the Warden-Hale system is assuming very simple parameters, but in order to eventually get it implemented on the Rio Tinto network, I'd have to look at what type of monitoring units I could find that would give me the speeds I want. And in the development of the algorithms, also utilise developed relays by companies such as ABB and see if they can actually integrate with the operational functions of the SPS.
My question, sorry, if I may continue. It was about, it's just a piece of software you have to integrate into the big SCADA system. It involves incorporating new equipment. My concern is safety. You see, how do you know your system is not going to introduce unknown side effects to an already operating system?
So the installation part wouldn't be too difficult. We've already got protection schemes in place with differential and comps there, so it'd just be a matter of hooking the SBS units up to those. But in terms of its operational sense to make sure it doesn't trip when it's not supposed to, we'd have to do advanced nuisance testing in software environments.
Let's thank our speaker one more time.